When a massive star, 1.3 to 3 times bigger than the Sun, explodes as a supernova, a neutron star is born. The massive star runs out of nuclear fuel and collapses under its weight, causing a tremendous explosion. Gravity then compacts the material, compressing the protons, electrons, and other subatomic particles to melt into each other to form neutrons. The only thing that remains is the dense inner core, about the size of a large city and heavier than the Sun. The neutron star rotates rapidly, producing beams of radiation that emit a wide range of energy. Due to their strong magnetic fields and rapid rotation, neutron stars yield intense electric fields, which further produces radiation. For a similar reason that true north and magnetic north are different on Earth, the magnetic and rotational axes of a pulsar are also misaligned. Therefore, the radiation sweeps around as the pulsar rotates, just as the spotlight in a lighthouse does. Like a ship in the ocean that seems only regular flashes of light, we see pulsars turn on and off as the beam sweeps over the Earth. Neutron stars for which we see such pulses are called pulsars.
In late 1967, the first pulsar was discovered by Jocelyn Bell Burnell, a graduate student who was pursuing a PhD at Cambridge University. After earning BS degree in physics at University of Glasgow, Bell assisted in the construction of a primitive radio telescope made of a massive array of poles and wires stretched out on a field. The radio telescopes were being used to track quasars, the massive and most distant objects yet discovered in the universe. Bell used to operate the telescope to analyze over 120 meters of chart paper every 4 days. After long days and nights, Bell detected a persistent noise in the data that she didn't seem to understand. The markings on the chart were unusual, fast and consistent to be quasar. It took a year to unravel that this regular blip was from a rapidly rotating neutron star known as pulsars today to us.
The pulsar was created just moments before a supernova took place in the Crab Nebula. The pulsar, also known as the Crab pulsar, is one of the youngest known to date. The observable energy range of pulsars goes from 0.1 to 100 giga-electron volts. Once it surpasses 100 giga-electron volts, it becomes much more difficult to detect. This is because the X-rays the pulsars emit become gamma rays, which are much more difficult to detect because of its smaller wavelength. Thanks to its wide field of view and high-duty cycle, HAWC is able to observe more than 100 of known gamma-ray pulsars for an extended period of time. The HAWC is located 4,100 meters above sea level in Puebla, Mexico, on the volcano La Sierra Negra. The HAWC consists of 300 tanks and spread out over an area of 22,000 meters squared, each containing 200 liters of ultra-pure water in a watertight bladder. One scientific goal of the HAWC is to search for pulsed very high energy gamma ray emissions from these pulsars. One challenge of HAWC for detecting pulsed emissions from pulsars is the higher contamination of cosmic ray events in the dataset. Most of the pulsars found in the strand of gamma ray detection were found through blind searches, but thanks to the HAWC observatory, we are able to detect higher levels of gamma rays and pulsars with higher energies of 100 giga-electron volt. Pulsars are rotating neutron stars that emit beams of light, and every time they do rotate, they move in and out of sight. They come in varied shapes and sizes, spewing X and gamma rays. They partake in beautiful cosmic dances that can enthrall you for days.
So from these wondrous objects, there is still a lot that can be learned. A myriad questions are left a begging, many stones still left unturned.